Suppose that we were in telephone conversation with a Martian or an Arcturian or something. We don't know where he is, and we would like to describe things to him. We want to tell him about things. We say, well, how is he going to understand the words? So that's been studied very much by Professor Morrison here. And he has pointed out that one way would be to start out and say, tick, tick, 2, tick, 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 3, and so on. And pretty soon the guy would catch on to the numbers. And then to understand your number system, then you can write lots of numbers, and you could, for example, write a whole sequence of numbers that represents the weights, the proportional weights of the different atoms in succession. And then say hydrogen, 1.00, deuterium, and so on. And he would, after he sat down with all those numbers and piddled around a while, would discover that the mathematical ratios were the same as the ratios of the weights of the elements, and therefore those names must refer to elements. And so gradually you could, in talking to him, have a common language. In many ways, common. There are many. Now comes the problem. Suppose that he says, you fellows, after we get familiar with him, he says, you're very nice. Now I'd like to know what you look like. And you start out, well, we're about 6 feet tall. He says, 6 feet, how big is a foot? It's very easy, you say. A foot, 6 feet tall, is 170,000 million hydrogen atoms high. Well, it's not a joke. It's a possible way of describing 6 feet to someone that has no measure, assuming that we cannot send them any samples, nor can we both look at the same object. We have to tell them how big we are, we can do it. That's because the laws of physics are not unchanged under a scale change. So we can use that fact, to use the properties of the scale to determine, you can use that fact to determine the scale. Well, here we describe ourselves after telling us 6 feet tall and we're so-and-so bilateral on the outside and we look like this and there are these prongs sticking out and all this. And he said, that's very interesting. What do you look like on the inside? So we describe a heart and so on, and we say, now put the heart in on the left side. Now the question is, how can we tell him which side is the left side? By what possible, you say, you take beet sugar, see, and you put it, in water, and it turns. Only trouble is he has no beets up there. Or we have no way of knowing whether the evolution, if it was even corresponding to the same proteins on Mars as here, whether the accidents of the evolution would have started with maybe the wrong-handed threads. So there's no way to tell. So after much thought, you see you can't do it. And so you conclude it's impossible. However, about 5 or 6 years ago, certain experiments indicated that they got reduced all kinds of puzzles. I won't go into detail. We got into tighter and tighter difficulties, more and more paradoxical situation, until somebody proposed, Li and Yang proposed, maybe the principle that right and left symmetry, that nature is the same for right and left, is not right. And that would help to explain a number of mysteries. And Li and Yang proposed some more direct experiments to demonstrate this, and I'll just mention the most direct of all the experiments. The easiest way to tell was experiment on, well, there were several first experiments which were quite clear, but the one that's easiest to explain is this, that when we have a radioactive disintegration, in which an electron and a neutrino are emitted. For example, this is one that we talked about before. Electron and antineutrino. Or this is a neutron disintegrating into a proton, electron, and an antineutrino. Or the corresponding thing can happen to a neutron and a nucleus. Anyway, there are many radioactivities in which the charge of the nucleus increases by 1 and an electron comes out. The thing that's interesting is that if you measure the spin, electrons are spinning as they come out. If you measure the spin, you find out that they're spinning to the left. That is a definite significance, that the electron, when it comes out of the disintegration, is turning this way. And that helical description is a left-hand thread. It's as though, in the beta decay, the gun that was shooting out the electron were a rifled gun. And there's two ways to rifle a gun, because there's a direction, out. And then there's a question, do you turn it this way or that way as you go out? And the experiment is that the electrons come from a rifled gun, rifled, twisted to the left. And so, using this fact, we can call up the Martian and say, listen, take radioactive stuff. Now, I would have prepared a particular example, a neutron. And look at the electrons which come from such a beta decay. And then you define left by this screw thread, and let's see, you let, it'll take me some while to figure out how to do it in detail. Say the electron's going up, and the direction of motion of the way it's spinning is into the body on the left side, and that's where the heart goes. Something like that. I'd have to think a little bit more of it.